and this is where we continue. Who can tell me what was the basis of Hartree-Fock, or the fundamental approximation we did in it?
Single determinant.
Exactly, we have only one determinant. So we know the real many-body wave function is not a single, it's many determinants. But since we cannot handle a near infinite number of them, we said let's look what happens if you have just one. Okay? And in fact, we were able to arrive at some solution in the sense that we found a closed form for the determinant. Okay? So we say we have a single determinant, which is a true many-body function. This depends on n coordinates and n spins for the n electrons. Okay? Now, what one needs to know to determine this is if we have n electrons, we need n orthonormal spin orbitals. Remember, these were these things which I call phi of x. Okay? So everyone is either spin up or spin down, and it has a given shape in space. And this is what you're used to from single particle quantum mechanics, because this is an orbital in space. It's just one coordinate, and it's not has no fermionic rules about exchange, because it's just for one single particle. Okay? So we need n of them. We need them to be orthonormal. And the best n possible ones, which we put into one determinant, are those which will give us the lowest energy. Okay? Now, last time we have written down the energy. So what we had done is we said we have this determinant given by the n functions phi I. We put this into the middle of our electronic Hamiltonian, and we calculate this, and we said this here, well, if we add the ionic energy, this is just the Coulomb repulsion between the nuclei, which has nothing to do with the electrons. This is what we call E Hartree-Fock. Okay? So we therefore found a closed expression for the Hartree-Fock energy as a function of those single particle orbitals. Okay. This is what we did last time, and I would like to write it again. So what our result was E Hartree-Fock, in fact, is it contains several parts. Okay, one part is everything which is related to the single particle operator, because this Hamiltonian here, as you know, has a single particle term, which is kinetic energy, which is interaction with the nuclei. Single particle in the sense that electronic coordinates appear only of one electron at a time. This is why it's called single particle. So this is kinetic energy and interaction with the nuclei. And then this Hamiltonian here has a two-body part, which is the Coulomb interaction R1 minus R21 over the distance between R1 minus R2, which is a two-body term. And correspondingly, we have here different parts in the Hamiltonian. And so the first part, the one of the single particle terms, we can simply write it as sum from 1 over me. So we sum over all electrons, we integrate over all space. Okay, and then we have phi I of R complex conjugate times minus h bar squared divided by 2m gradient squared minus the interaction with the nuclei, which is something like this, divided by R minus the position of the nuclei times phi. So this was one part of the Hartree-Fock energy. If you look again at your notes from Monday, you will find precisely this. And the sum here is over all the n spin orbitals which we have, which we assume to be orthonormal. And we said that there one doesn't need to manipulate huge determinants and so on, because one could have guessed, in fact, that the kinetic energy is simply the sum of the kinetic energies of each of the orbitals. And here you see the interaction with the nucleus is the sum, again, the sum over all electrons. And for each electron, you calculate the interaction with the given nucleus. Okay? So this is what one could have guessed. Okay. What is more difficult to guess was the next terms, which come from the electron-electron part in the Hamiltonian. And you remember that because there are two terms in the electronic Hamiltonian, R1 and R2, then we could not say that of all the permutations which appear on the left and on the right hand side. We couldn't say these must now be the same permutations as it was the case here, because there was the possibility that in one case you have I and j in position 1 and 2, and here you could have j and 1, so the two opposite. Okay. So the fact that we have determinants lead to the fact that the two-body term ends up giving us two terms, and these two terms are conventionally called the Hartree term and the Fock term. This is Hartree-Fock. Okay? And these terms are, if I write them, one of them is very easy. It's plus 1/2 integral over all space. How do I call it? The variables d3r, d3r prime, and then we have the density at position r, density at position r prime, divided by distance. Okay. Where this thing here, the density, is, as one would have expected, simply the sum over all electrons again, and it is at this position the norm squared. Or, because that will be useful in a second, we can write it as 1 e by I at position r. So we define the electronic density at a given point r as being, as one would have also guessed, we have n spin orbitals, and we take the norm squared of each spin orbital at the given point. We sum over all electrons. This gives us the density at this point. And we have had in this term here, this is the Hartree term, we simply have kind of a classical Coulomb interaction between a density at one point, the density at another point, divided by the distance. So this is simply a Coulomb interaction between densities, and we sum over all points here. So this here is Hartree.
Excuse me.
Yes.
I don't know if I forgot that or not, but since it's a continuous integral in the second term, there is a singularity when it can be r equals to r prime.
Exactly. So when you have r equals r prime, in principle, the integrand is infinite. But this is an integrand which you can integrate over. So this is not a problem in this case. So because in 3 dimensions, if you take a 3-dimensional integral, imagine you do it, so you have here the position, okay? And you integrate over the phi psi theta d theta times r squared dr. Okay, so this here would be an integral over. And now if as an integral you have 1 over r, so the 1 over r singularity, okay, then this thing here cancels. Or you're left with this, and you at r equals 0, the integral has some finite value. This is why this is not known. Okay, so as it's written here, the density at each of these points, each one is the sum over all our n spin orbitals. So since we have here one sum times here the next sum, we have included here, remember this term where here we have the same spin orbital as here. Okay? So if here you have the sum over I as I've written, here we write the sum and you call, for example, the index j, then you have here in this implicitly written the term where I equals j. Okay? This you have, but this is not a problem. We said we may add this term, which in the beginning was not here, because in the Fock term, the term which now comes with the opposite sign, we also add this term, and therefore we make no mistake. Okay. Just why this might be a problem, you can already see. Imagine you have only one single electron. Okay. If you apply this to a determinant which contains only one orbital, so all single particles, obviously one electron never interacts with itself. An electron flies around in space, it interacts with the nuclei, it has a kinetic energy, but doesn't interact with itself. But it has a density. So for one single electron, you would here have in the energy a term which is the density of one electron which interacts with itself. So it cannot be. And this is why here in principle we have something which is called a self-interaction term, that an electron, the I equals J, or if you have only one electron, this comes only from one electron, would interact with itself. But luckily we have the same term with the negative sign in the next term, so here this is not a problem. But keep this in mind, this so-called self-interaction, that if you had only one electron, this term here is not zero, even though when you solved, I don't know, the single particle harmonic oscillator or the single particle hydrogen atom, you never had that your electron is interacting with itself, no? Because it doesn't do it. Okay? So, this is the Hartree term. Now, and we have clearly a classical analog to understand it. The Hartree term looks like a classical Coulomb interaction between densities. Very simple. What does not have such a classical analog is the Fock term, which is for this reason much hated by people, and we can write this is a sum over I and J, both go from 1 to n, and we allow I equals J. We explicitly have to allow it because we've allowed it here. We want this to go away. Again, we have a double integral over dr prime. And now instead of density here and density there, we have something which is phi I complex conjugate at r times phi j at the same position. And we have at the other position, we have phi j complex conjugate at r prime phi I prime. And we divide by r minus r prime. This term here is Fock. Or also called exchange. It's called the exchange term because this comes, if you remember, you had the two determinants, and this term arises when in one of the two permutations you have the pair I and J exchanged. So this is the exchange term, or the Fock term, or some people call it the Fock exchange term, whatever. And let's have a little bit a closer look. So you see, it looks a little bit like the Hartree term. So if this here was a density, then it is like the Hartree term. It's a density at position r times the density at position r prime divided by the distance. Only that this is not a density. What this here is it's not phi I star times phi I, it is for a different pair of orbitals. And therefore we cannot write this here in terms of some density or something. Here really explicitly these Hartree-Fock single particle orbitals appear. So whatever this is, but this is the mathematical form which we found. And then we have to add, so these were the terms, and then obviously we add the I and I interrelation to it, which is true. So the I and I interaction does not depend on what the electrons do, therefore we don't care very much. Okay, so this is essentially written in a slightly different way, where we ended on Monday. Any questions to this? No? Okay, so now anyone who wants to do Hartree-Fock must find, obviously, those phi i's. You see, this is all as a function of these phi i's, of the orthonormal orbitals. Now we must find those phi i's which bring us this energy to its minimum. Okay? And then we have found the best possible single particle orbitals which give us the best approximation for the energy. This is the Hartree-Fock energy. So now, how do we do this? Well, we have to minimize this energy with respect to the orbitals, being careful that the orbitals must stay orthonormal. Okay? So what we have to minimize is the following. We have to minimize E Hartree-Fock, as we have just written, which is a functional of all the single particle orbitals. But we have to keep those orthonormal. So what one does normally is one writes this here minus a sum over ij lambda ij phi I phi j minus delta ij, and this object here must go to the minimum. So what is this? On one hand, this here is the quantity we want to minimize, Hartree-Fock energy. Okay? And we want to find those orbitals which minimize. But at the same time, since they need to stay orthonormal, one adds what are so-called Lagrange multipliers. I'm sure you've heard many times about Lagrange multipliers. And the way one adds a Lagrange multiplier for one constraint is one adds lambda, or say a number, times the thing which you want to keep to 0. So what you want to keep to 0, since the phi i's and phi j need to be orthonormal, it's the scalar product of orbital phi I and phi j. It must be delta ij. It must be 1 if I equals j, normalized, and it must be 0 if I different from j. So this object here, phi I, phi j, minus delta j, this must be 0. Okay? How many constraints do we have? Well, we have n square constraints, because you have n square constraints for each I and for each j. You have one constraint. And so we call the Lagrange multipliers are these lambdas here, and here every time the thing which must be 0. So we minimize this. This is our goal or our duty now. And this leads to something which is quite interesting. So if I take this here, and now I calculate the derivative of this with respect to phi, to any of the phi's, let me call the index to which I derive it, to phi k at some position r1. Okay? So I take this equation and I derive it with, let me even do this here, with respect to the complex conjugate of orbital number k at a position r1. Okay? So the phi's are there, the unknown, and I take this expression which I have and I derive it with respect to phi star. I will do it with respect to all orbitals, of course, but now let me write it explicitly for orbital number k, and k can be any number between 1 and n, at any one position, which I call n. Obviously, if you want to minimize, our rule must be that this derivative must be 0. Okay? Then at least we are at a stationary point.
Excuse me.
Yes.
You said there are n square constraints, but aren't these
It's not n square, in fact. It's n times n minus 1 over 2 squared. Because the constraint I, j is the same as j, I. Okay. So, deriving with respect to the complex conjugate of any of these orbitals, for example, the first part is very easy. Here we have explicitly an integral over all space, a sum of all electrons. So now if I have chosen electron number k, okay, or the orbital number k, in the position r1, then here the only term where this is non-zero is if I equals k, and if my position is r1, the one I've chosen. Okay? So then I have here this appears simply in a linear form. So the derivative will be this here at the position r1 for I equals k. Okay? So this derivative will be, where shall I write it? So we'll get a lot of terms. We will have minus h bar squared divided by 2m. The second derivative minus sum of all nuclei e squared ci divided by, and now the position is the r1 where I derive r1 minus I acting on phi k r1. This is one of the terms which appear. Okay. So I've simply taken this line here and derived it with respect to this. The sum and the integral go away. We are left with this here taken at the position I equals k and r equals r1. And this is what I have here. Then, here, seemingly we do not have any of the orbitals, but we have them because the density is simply written in terms of this. So if we derive the density with respect to phi k, then also here the sum goes away, and I'm left with phi k at r1. Okay? So I take the derivative with respect to n, and then chain rule, I derive n with respect to phi k. So I have this here, times phi k at R1, and then this one, so the factor 1/2 goes away because I have twice the same term. So the half term will give me minus an integral d3r prime. So one of the two integrals goes away because I take, for example, r to be the r1 where I derive, and then only one of the integrals is left. And I have n at the position r prime divided by r1 minus r prime times phi k r1. Okay, again, so this is the term, like it's written here, derived with respect to n at r, and then I derive n of r with respect to phi star, chain rule, and obtain this. And the factor 1/2 again goes away because I have this and that. Now here I've written, in the last term, I've written everything explicitly in terms of those, so here it's easy. So again we will have two terms. Once we have I equals k, and the sum goes away, and the other case we have j equals k. And every time the other sum remains. Okay? So what this here will give us is minus. Again, I can already tell you that the two terms where you derive here will lead to exactly the same term as the one here. So the factor 1/2 goes away. You can check that as homework. And then you find what is you're left with, again, an integral 3 over r1. In this case, one of the two sums also remains. And you have phi j at r1 times phi j at r prime divided by r1 minus r prime multiplied with phi k at r prime.
I think I missed how the factor 1/2 goes away.
In this term or in this term?
Is the
In the first one?
yes, yes, yes.
Okay. So you derive with respect to n of r. Okay. Then you find what we have written here. Okay. And then you derive chain rule n of r with respect to phi k, and you will get a phi k at r1. Okay. This is once this term. Then now you derive, also this here can be n of r1, to which we want to derive. So then you derive with respect to this. Okay. Now the integral over r prime disappears and the integral over r is left. But we can rename it r prime if we want. So we are then left with this term here which remains, and this here gives us again a phi k star. So we get twice the same thing, just by renaming. And in this term here, in the Fock term, we have exactly the same. So let me just say something about, again, how this here looks. So we were deriving with respect to k, and you see that here we have something which is acting on the orbital phi k at r prime. We are integrating over all space and multiplicating phi k with any of the other orbitals. Okay. What we get, we make this integral here with respect to position r1, we multiply it by phi j. Sometimes this here is written in the shorthand notation as phi j divided by r1 minus r prime. I do not like this notation because here there is position notation and this is mixed. What is really meant is what I've written. So these are the derivatives of these terms. The ionic term obviously does not depend on electrons, so nothing happens. Now we derive this here. This here is simply an integral d3r of phi I complex conjugate of r phi j of r. Okay. So deriving this term here with respect to phi complex conjugate k means that I equals k, and we put this on the other side, so we can write here. This here is therefore sum over j lambda k j times phi phi k at 1. So what we have obtained is some operator acting on phi k, and here also some operators acting always on phi k equals a number times phi k. Okay? So it is now very natural to say all these things here which act on phi k, they look like, say, one operator. This is what is called the Hartree-Fock Hamiltonian. So our minimization leads us to the fact that these orbitals, our unknown orbitals, have to, so the Hartree-Fock spin orbitals have to obey the following equation. The equation is that the Hartree-Fock Hamiltonian times the orbital phi k must be sum over j lambda k j times phi j. And this H Hartree-Fock is very important. Hartree-Fock Hamiltonian is a single particle term minus integral d3r prime and r prime divided by r minus r prime d3r prime, and here we have also the sum over j phi j of r phi j r prime divided by okay, so this here is the Hartree-Fock Hamiltonian. You see, all these operators, they simply act on phi k. And now there's one interesting thing which one can do to simplify this here. Still, we do not like that here we have a matrix. We would like this to be an eigenvalue equation. But now comes something which I do not show you here, but which you can show easily if you want.
Excuse me.
Yes?
I think that should be k index over there. In phi.
Kj? No, it must be like this.
But
have I written it wrong? Yeah, here I've written it wrong. Because you see, here you have the sum over ij. Then you choose that I is k, okay? So you have k, j, and here you have phi j. So one thing which I cannot show you, but which I just tell you, is that the Hartree-Fock is independent of the unitary rotation amongst our phi I orbitals. You know what a unitary rotation is. It is essentially you take other linear combinations of the same orbitals, and whatever other combinations you make of these n orbitals, the energy is not changed. Why is this important? Because now you can choose here any rotation of these orbitals such that this matrix here becomes a diagonal matrix. And then you can write H Hartree-Fock times phi k is epsilon k times phi k. Okay, so if this here becomes a diagonal matrix instead of a complete matrix, then these Lagrange multipliers, they can simply be eigenvalues. This is something I have not shown it, I ask you to believe it, but this is what comes. So in the very end, Hartree-Fock theory, where we start, we have an approximation to the many-body wave function as a single determinant. It leads us to an expression for the energy. Minimizing the expression for the energy with respect to the unknown orbitals brings us to an equation which looks like a Schrödinger equation for the orbitals. And now you see here, this is something which we are very much used to. It's a Schrödinger equation for orbitals, and we must find the n lowest eigenvectors of this operator. Okay? So it looks quite easy. Instead of having many body wave functions, so we need n yet unknown orbitals, but these orbitals are eigenvalue, eigenfunctions of a well-defined operator. Okay. So far, any questions? Because I will have to say many things about this. So, but the basic idea you understand. Okay, we want to approximate the many-body functions with one determinant. For doing this, we need to know what they are. We've written the energy, we minimize it, and we find an equation which they satisfy. So we look for the n lowermost eigenfunctions of this operator here. Each one has an eigenvalue, but it doesn't matter. What is important is we find the n lowest ones, and with those n lowest ones we can plug it into our Hartree-Fock energy, and this will be our approximation to the electronic energy of our system. Okay? So far it all looks nice. But now there are several things where you as students you must be extremely careful. On this blackboard there are two Hamiltonians. One is this here, this is the real, after the Born-Oppenheimer approximation, the many-body Hamiltonian acting on a many-body wave function. The Hartree-Fock Hamiltonian, it appears in the context of solving a many-body problem, but this is not an operator which acts on a many-body wave function. This is a single particle operator which acts on a single spin orbital. So please understand that this is something completely different. These live in different Hilbert spaces. This Hamiltonian lives in the Hilbert space of n-body wave functions, for example, a determinant or sum of determinant, whatever. So this Hamiltonian acts in the Hilbert space of the complicated many-body wave functions. And we have seen it, it looks quite easy, this one, because it is just kinetic energy potential and then 1 over R1 minus R2. So this has an easy form and it acts on many body functions. The Hartree-Fock Hamiltonian, it has formally a much more complicated form, okay, but it does not ever act on a single body wave function, on a many body wave function. It acts only, and it can act only on single body wave function. You see, it depends on R1, R2. It's an operator of R1, R2. It's not an operator which depends on R1, R2, and then so it's a single body operator. So this is something, never ever forget this. Also later we have, by doing the Hartree-Fock approximation, we gained something very valuable because we were able to go from a many-body world where everything is complicated to a single particle world where we have an equation for the single particles. And then solving this here, plugging this again into a determinant, then we have an approximation to the many-body wave function, and the expectation value is precisely the Hartree-Fock energy. Okay? So keep in mind, this is a single body. What is the meaning of those? Okay? So it has eigenfunctions, we need them, we need the lowest n ones, but it has also eigenvalues. Now, never ever think that these epsilons here, the eigenvalues of the Hartree-Fock Hamiltonian, they are not the Hartree-Fock energies. The Hartree-Fock energy is this object here, which depends on exactly the way we have written it down, on the orbitals. Okay? So this is the Hartree-Fock energy. The eigenvalues which appear here, they are merely objects, they are Lagrange multipliers for keeping these things orthonormal. These here are not Hartree-Fock energies. Okay? So sometimes people, so you can obviously then plot those energies. Here you have Hamiltonian, and then you can check what are the eigenvalues of that Hamiltonian, and you can plot them. So you can have energy, and you say, okay, I have this value, this value, this value, this value. And obviously what one does in order to find the lowest ones, one takes one spin up here, one spin down, one spin up, one spin down, until you have arrived at your n orbitals. Okay? So for example, if you have 8 electrons, you would take these here, and the other eigenvalues you leave empty. Okay? So this is how you determine which of the single particle orbitals you choose. You choose those which correspond to the lowest energies, to the lowest eigenvalues. But none of these energies here is the Hartree-Fock energy. The Hartree-Fock energy is the complete energy of everything, determined once you choose which orbitals you have. So the value of these energies is nothing. Sometimes people say, well, but they have a meaning, these epsilon, so I should not write here, I should here write the epsilon, so the eigenvalues of the Hartree-Fock Hamiltonian. They kind of have something to do with electronic excitations. Because if the electrons are not in their lowest possible state, but if, for example, you take this electron, instead of putting it here, you put it here, okay, then you're not in the lowest possible state, but you are in some excited state. So some people say, these here, for example, the difference between the uppermost occupied and the lowest unoccupied, that this would be the gap, the electronic gap of your system also. So sometimes people interpret these epsilon values as excitation energies, but this is not justified, because the truth is these are not supposed to be eigenenergies of anything, they are just Lagrange multipliers. And in fact they are very, very bad approximations for the eigenenergies. Okay? So the Hartree-Fock energy is this one. The Hartree-Fock energies are not those. These here are simply determined to say which of the orbitals of the eigenvalues we occupy. So this is one of the things which I want to say. This is a single body operator, this is a many body operator. But here difficult to solve, here easier to solve. But still I say easy to solve, it's not so easy to solve. Because I left it here in the center of the blackboard. Look at this thing here. So what we need to do is we somehow put into the computer this operator. Okay? So you plug this operator into a computer and you calculate its eigenfunctions and eigenenergies. However, in order to plug this in where you have the kinetic energy, easy. You have this here, easy. But you need to write the Hamiltonian itself, the Hartree-Fock Hamiltonian, you need to know the density, and you need to know the orbitals. How is this possible? Because the orbitals are what you gain by solving the eigenvectors for this. So the problem of Hartree-Fock and of, in fact, many things in electronic structure theory, the problem is that we are in a kind of a circular problem. Okay? So in order to write the equation we need to solve, we already need its solution. Okay? So in principle we need the solution of this equation because we need the phi's. In order to be able to write the equation itself, because in H the solution appears. So this is called sometimes a self-consistency problem. Self-consistency means that you have something meaningful only if the density and orbitals you plug into this H operator are the same as the ones which you get out when you diagonalize it. And this is not trivial generally. So you understand where the problem comes from? We ended up with an equation which, to write it down, you already need to have its solution. Seems impossible, well, it's not impossible, but obviously it's a difficult. Okay? Good. So, now we see how this is done by doing self-consistency. itself. Consistent field procedure. Okay, the problem is the Hartree-Fock Hamiltonian depends on the phi I, and these single particle orbitals are the solutions to H Hartree-Fock times phi I is epsilon I. So the way how this is normally done, there are basically two ways to do it, but in most of the cases one does the following. One solves it, solution, with the iterations, iterative procedure. So this iterative procedure works like the following. At the beginning, you guess some orbitals phi I, and we call those of iteration number 0. So you guess how they might look like. How do you guess? Well, you could just say, okay, I start with the atomic orbitals. So for the given atoms I have in my system, there's a carbon, I get the carbon 1s, the carbon 2p, the carbon 3d, and so on, I don't know. Some hydrogen, I take the hydrogen 1s, so I take n atomic orbitals, orthonormal, and this is my guess. I know the solution will not be it, but I start by guessing. Another good way to guess, and often even preferable, is to take random numbers. Okay, so take a random number generator and you take some functions which you make orthonormal, which are just random noise, something. So you must just start with these here. The only condition, obviously, is they must be orthonormal. Phi I, phi j of the guess, they must be delta I. Apart from this, you can take anything. So then you set the iteration n to 0, and you start. You build your Hartree-Fock Hamiltonian of iteration n, and you do this using the orbitals phi I of iteration n, in our case of iteration 0. Okay, so you build the 0th iteration Hamiltonian using the 0th iteration guess. Then you use this Hamiltonian and you solve. H Hartree-Fock of iteration n times phi I call them out, is epsilon I phi I out. Okay, so this gives you now some orthonormal orbitals phi I out. Generally, they will be different from your guessed ones. You get now some orbitals. Then you check, is phi I out, is this, to some criteria which you can choose, similar enough to the phi I n you have used? Yes? Then this is your solution. So if what you have plugged into the Hamiltonian is what you get out of the Hamiltonian, then you are self-consistent. And then you can calculate the E Hartree-Fock with those orbitals, with the phi n. But generally this will not be the case, especially if you start here with random numbers or with simply atomic orbitals or something, then the out orbitals will not at all look like the random numbers you plugged in. So if they are not the same, what are you then doing? Well, you could say, well, you put those out orbitals and you build a new Hamiltonian in the next iteration. Would not work. Because this leads to some strange oscillations in your solutions and you will never arrive at the thing that they are the same. What one needs to do is you do a mixing procedure. So you say that phi, your next guess for n plus 1, will be alpha times phi I out, the one you just got, plus 1 minus alpha times the ones you had before. So this means with mixing, there are many more sophisticated mixing procedures, but they all have in common that as a next guess, one does not take just what comes out, but one takes a little fraction of it, so alpha is a number between 0 and 1. One takes a little part of what one has just obtained, and the other part one takes from what one had before. So one keeps some memory of what you had before. You can imagine this as if you had a damped oscillator. Without this damping, this would always oscillate between some solutions and it would never be the same. This damping that you keep memory of where you were before, this means that with some iterations the differences slowly become smaller. Mixing process, so you mix it, then you orthonormalize it, because simply this here you can immediately see this will probably not be exactly orthonormal, so you orthonormalize this with something, and then you set n towards n plus 1, and you end. Okay? So this is a cycle. You start with some guess, you build a Hamiltonian, you get a solution, you check, is this the same as with what I started with? Typically it will not be. Then you build a new guess, and the new guess is what you have just calculated, plus a fraction of what you had before, and then you restart this. So this can take, as a function of, it depends a bit on the physical properties of your system. This can take 10 iterations, sometimes it takes 100 iterations, it depends. But typically this convergence is easily achieved. And once you have convergence achieved, then you have the Hartree-Fock.
But what guarantees the convergence? For example,
nothing guarantees.
So it's basically hit and drag kind of thing.
Yeah. So it is not guaranteed that this will converge. And if it converges and how it converges depends very much on how sophisticated your mixing procedure is. And typically, so this is the easiest mixing procedure. One can in fact show that there are some very complicated ways of mixing, but the more complicated way the mixing is, the faster you can get to convergence, but the less convergence is guaranteed. You know, to guarantee it, I don't know if this very easy way can guarantee it or not, but I think it is never guaranteed. If there is really a problem and that it's impossible to make the iterative solution to the self-consistent field converge, then there is a second way, not doing it iteratively, but minimizing directly the Hartree-Fock energy with respect to n orthonormal orbitals. So there's a second way of doing it, but for all practical purposes, it always converges.
And I think it also depends upon how well we guess our phi 0.
Yes, obviously, it depends on how well this is. But this is less a problem of is it converges or not. If you choose very poorly your phi 0, it might be that you end up in a state which is not the minimum, that you end up in a local minimum which is not the global minimum. Okay? So this is why it's even a very good idea to start with random numbers. Because if you have just random numbers which do not look like something physical which you imagine, then it's very likely that these random numbers have a non-zero overlap with the exact solution, so they will go to the lowest one. If you take atomic orbitals, then you might need less iterations because you have already a lot of physics built in. But that physics might perhaps have, for example, a wrong symmetry. So you go to the lowest state with that symmetry which you have plugged in here, and then it might be that this is not the total global minimum.
So when you said you take random numbers, do you really mean numbers? Because how can number take a functional form?
This I will just talk about next. You remember that we talked about basis sets?
Yes.
Okay. So the numbers are the expansion coefficients in the basis set. So
okay,
each one of these spin orbitals phi I of r is a sum C r alpha and then a basis function alpha of r. Okay? And these expansion coefficients here, they are the ones which you choose randomly. Yes.
Are these phi i's like wavelength?
Sorry?
Are they like waves? Like they take one wave, then waves?
Yeah, so if you have plane waves, then these basis functions here would be plane waves.
If that really happens, then I don't think that multiplying the wave function by just a factor really changes much. It's just like a phase in front of it.
No. So what these are here is you put a number. No. So what you have is a whole function. So you have this function here multiplied with the number plus some other function. Okay.
Still a wave. Still like a plane wave, which is...
No. The phi's are not the plane waves, the b's are the plane waves. So this phi in the base of plane wave, it can have any shape. Okay, so this phi here, don't be fooled by the fact that here you might have waves or you have localized functions or whatever. Even if these are plane waves, you can represent as linear combination of them any shape of your function phi. So a function phi, which for example is here large and then goes to 0 here, this can be written as a linear combination of plane waves, which are everywhere. And now if you have this function here, and you mix it with the function which is localized a little bit here, yes, then it will move a little bit there. It's not that you're mixing plane waves, you're mixing the phi.
What I was thinking is like, really, if maybe we are dealing with really plane waves.
Yes, so if the b's are plane waves, this is what we
then
mean.
even if you make a linear combination of them, remain with another plane wave, and I don't expect.
No linear. Wait a minute. The linear combination of plane waves is not a plane wave. If you have e to the I g1x plus e to the I j2x, this is not a plane wave.
Oh, yes.
One more thing. In this mixing procedure,
Yes.
both phi out and phi n are expanded in B, right? BL.
Yeah. I mean, all of our phi's, everything is always expanded in basis.
So basically, we can like do something here and there will be like some C as a function of alpha.
Exactly.
A new coefficient.
Yes.
So what's unique about this particular mixing procedure? Can we just write, because we have expansion coefficient and the particular base for that thing. So here it would be, we are introducing a new variable alpha by this mixing procedure in a certain fashion.
No, not really, because the basis set remains unchanged. You always say the phi's are in that given basis set.
The coefficient will change.
So you can either say what you are mixing are the coefficients, and close your eyes in front of it. These are coefficients in front of plane waves or coefficients in front of delta functions or atomic orbitals. You could just close your eyes and simply mix and say, I say that the Ci at the next iteration on this basis function will be its value it had said before plus what has come out of. Okay, you could with alpha and 1 minus alpha. Okay. So you could choose to mix simply the coefficient. This is one way of mixing. Or you can say, but I know they are in front of, for example, a very short wavelength basis function or long wavelength basis function, and then adapt the alpha to that. This is what is often done, in fact, because if you have plane waves, you can show that the convergence behavior is different, so one chooses different mixing rates, different alphas for different values of the G in the basis function. But in the simplest and easiest of all mixing, and that which nearly always converges, is one simply takes the coefficient, closes the eyes, that there are coefficients in front of that function or that function, and simply mixes those coefficients.
Okay, so it's just like taking a factor from this one and taking a factor from the previous one.
Yeah. Exactly. So the self-consistency is important, and it is, if you use a code, it is what you see most of the time. You see the code, it says, okay, now I'm creating the basis set done in 2 seconds. Then I'm creating this and that. But then what you wait until when you wait for the result, what you wait a long time for is, it says iteration 1, error this. Iteration 2, error that. Iteration 3, and you wait until the error is small enough to be under, and then you know, okay, now this thing is. And this self-consistent field procedure, it's not a feature only of Hartree-Fock. Yes, in Hartree-Fock we have seen now for the first time. But next thing we will do density function theory. Same issue there. We will find something which looks like Hamiltonian, which depends on the solution, and we will also have to do iterations there. So any electronic structure computer program which you use, you will always find in the output that this is what you're waiting for, that you have some iterations and you wait until it converges. Okay? So, since you asked, I wonder if I should write everything in terms of the basis functions or not. So, no, I think, you see, one can now say, okay, we have in the Hartree-Fock Hamiltonian kinetic energy and all these terms we've identified. We could now write in these expressions all terms where phi appears in terms of an expansion, in terms of the basis functions, and then find which matrix function one finds. But I think it's probably not necessary to do this. Or would you like to see it or not? How to go towards a matrix equation from these equations on the phis? You choose. You want to see it? Okay. So now we introduce our basis functions. In Hartree-Fock. Again, so the basis function is such that our spin orbital phi I of r is written as a sum over alpha ci alpha times the basis function b alpha. Okay? And as we have said, those can be chosen either blindly as plane waves or something which does not depend on your system, or they can be chosen in a more chemically intuitive way as atomic orbitals, for example, of your system, or something which you know about the system in order to have less. Obviously, you will have much less basis functions, and therefore everything easier if you choose basis functions which look already like the assumed solution of your system. But you might make a mistake because perhaps the solution is different from what you think its shape might be. And if you take plane waves or just a grid in space, then you assume nothing. You have the most general solution, but the price to base you will need many more basis functions, so everything is heavier. Depends on what one wants. So this is what we have. And then we have different terms in the energy. So we have the kinetic energy. the kinetic energy was minus h bar squared divided by 2m, sum over all orbitals, phi I, second derivative phi I. Okay. Now, we write each one of these here as a linear combination of basis functions. And then this here becomes minus h bar squared divided by 2n. We remain with the sum over I, and we sum over alpha and beta. Why two sums? Because phi I is a sum, say over alpha. Here we have again phi I, and we have a different sum, so we must name it with a different index. I call it beta. And then we have Ci alpha, complex conjugate, Ci beta. And here we have the basis function alpha times second derivative basis function. So since the basis functions are things which we know, for example plane waves or so, this is something we can, without needing to know the solution of our system, this is we can always calculate. So for example, if this here would be e to the I j r, then the second derivative would be simply g squared. So this here is a matrix. The dimension of the matrix is the number of basis functions you have. And I call this here T alpha beta. So what we have here is this is minus h bar squared. I take also these factors here into this. So this here is then sum over I over alpha and beta, Ci alpha, Ci beta, T alpha. The external one is also very easy. So minus sum over all orbitals, sum over all nuclei, Ci e squared divided by r minus r I times phi I r star and we integrate this. And this then gives you also sum over I and alpha and beta, Ci alpha star, Ci beta, integral over all space, sum over all nuclei, Ci e squared divided by r minus ri times basis function alpha times basis function beta. This is minus sign, and I call this Vx alpha beta. So here I find that this is sum over I, alpha and beta, Ci alpha, Ci beta, Vx. Now these are real numbers. So when you try to minimize your energy, you now only have to minimize with respect to these numbers. This a computer can do. And these here are now matrices. And once you have chosen what your basis functions are, the first thing you need to calculate, independently of your solution, is all these matrices. The kinetic energy matrix, the external potential matrix, and so on. Now, much more complicated, but not really difficult. It is complicated because one gets always all indices wrong, and when it's the first time, is Hartree and Fock. So the Hartree energy will be 1/2 with a sum over all I and j. I can obviously now not write in terms of the density because I expand the orbitals in terms of the basis function. So let me write this really in terms of that here. So sum over ij. Now remember, in the Hartree term I have phi I star phi I, phi j star phi j. So I have 4 times each orbital, so will I have 4 times this sum. So I will have a quadruple sum over basis functions. This is alpha, beta, gamma, and delta. Then I have Ci alpha, complex conjugate, Ci beta. So this comes from phi I, complex conjugate, phi I. Okay. And then I have Cj, complex conjugate, gamma, Cj delta. And here come the double integrals. Duck, duck. B alpha of R, B beta R, B gamma of R prime, and delta of R prime divided by R minus R prime, 3R, 3R prime. Why this? Because you have phi I at the position R times the same phi I at the same position. So here we have those at R. And then we have phi j are both taken at the position R prime. So here you have this. And this integral, which depends on 4 indices, they are called, they have a name. So they are E. Obviously, so you integrate over all space. Now all space dependencies and all go away. This is E alpha beta gamma delta, and they have a name. They are called electron repulsion integrals. ERIs. And they are, sorry?
Shouldn't that be complex functions?
The basis functions are most of the time real functions. So if they are localized, otherwise, yes, otherwise you would have here complex conjugate. The problem is, you see, if you have 10 to the 4 basis function in your system, for example, here you have how many of these numbers do you have to calculate, how many integrals do you have to calculate? 10 to the 4, 8, 12, 10 to the 16 integrals you have to calculate. Can be quite tough. So this is a computation and a memory bottleneck for your codes. Okay? It's especially a memory bottleneck. Very often the integrals, they can be calculated very quickly, either because one knows what they are analytically, or they are very easy formulas, so a computer can do this very quickly. But storing them in the computer needs a lot of memory. So imagine 10 to the 16 real numbers to store, just to have this matrix stored in a computer. This is already a big feat. So for this reason, either one uses such, for example, Gaussian basis sets, which are localized, which give you chemical intuition, where you need only few basis functions. If you use few basis functions, then it's not 10 to the 4, then it works with 100 basis function, and then 100 to the power 4 you can easily do. Okay, so either one does this thing here with the basis function where one needs to calculate the integral, but one has few of them, or one takes basis function where these integrals here, they Newton dependently calculate because they are, for example, super easy. With plane waves, these things are super easy. Because here you have a plane wave times another plane wave gives you a plane wave. Here you have also plane wave, so here you have plane wave and plane wave. And calculating the Coulomb term of a plane wave with the g is simply 1 over g squared in Fourier space. So you do not need to calculate, if you have plane waves, you do not need to calculate anything, and you have those integrals already. So you do not need even to, you just look at the indices, this is, what is the g of that plane wave, what are the 4 g's of the 4 plane waves, and you immediately know what it is. Okay? So there you do not need to store anything. This is why you can handle huge numbers of plane waves, because you never need to store or to calculate it, because you know it analytically. If you have atomic orbitals or Gaussian functions, then you need to calculate them, but then luckily you have much less and you can live with this form of power. Okay, so here we now have, we can write this here as 1/2 sum over I, sum over alpha beta, B R3 alpha beta, Ci alpha complex conjugate Ci beta. Why do I write it like this? Because writing it like this, it just looks like this term and this term. It looks like this, Ci alpha z times beta times a matrix, which is just a square matrix. But now my V alpha beta, my Hartree term here, my Hartree potential, it is itself a sum over J and a sum over gamma delta of C J gamma complex conjugate C J delta E alpha beta gamma delta. So here comes in the self-consistency we've noticed, okay? Because obviously the Hartree-Fock Hamiltonian, the single particle Hamiltonian will be T plus Vx plus V Hartree and then plus V Fock. So these are all single particle operators which act simply on this here. But to know the Hamiltonian, to know the Hartree potential which goes in, you need to know its solution, the C's. You see, here it's again self-consistency. You cannot get around the fact that here the potential depends self-consistency. So in this language, when we say in the beginning we guess what our single particle orbitals look like, this means we guessed some numbers C, some expansion coefficients. With these guessed numbers, it can be random numbers, and now everyone believes me, these are numbers, okay? These are not functions. With these guessed numbers here, I can build a VH. Knowing VH, I put it together with the T and with the external and then with the Fock term. I get a Hamiltonian, I solve the Hamiltonian, so the Hamiltonian is a matrix. I get the eigenfunctions of the matrix, and they will be typically different from what I've plugged in here. I have to mix, and then I build a So this was Hartree, and now exchange. So exchange, we again have sum 1/2 sum over ij, sum alpha beta gamma delta, Ci alpha complex conjugate, Cj, now I write delta, Cj gamma complex conjugate, and Ci delta. So you can write with any order of these indices you want, only you must not get then all the integrals wrong, but here I have the same kind of integrals then as we have had before, and the order now is alpha delta and gamma delta. So if you wonder why this order of alpha beta gamma delta and here this one, just write it down, everything what we have seen before, and you fill out. So, but easily gets it wrong. Probably this might be wrong. I think it's not wrong because I've corrected already once. So we can write this here then as 1/2 sum over I. No, not 1/2. So simply sum over I, sum over alpha and beta, Ci alpha complex conjugate Ci beta. V alpha beta exchange or fork order. And this term here, V alpha beta of the exchange is sum over all j, sum over gamma delta, Cj gamma, Cj delta, E alpha delta gamma. Again, self-consistency, you need to know the C's. You need to know the C's in order to write what is the exchange term. But now this allows us to say E Hartree Fock is very simply sum over I and alpha and beta Ci alpha complex conjugate, and here we have T alpha beta plus V external alpha beta plus V Hartree alpha beta plus V exchange alpha beta times Ci beta plus the I. So now, thanks to the fact that we've introduced the basis function, now you see this is really all matrix algebra. You have here a matrix, which is the sum of 4 matrices. To the left and to the right you have, you calculate the, so you take the matrix times a vector, which gives you a vector. Take the scalar product with the vector itself, this gives you a number. Okay? This is the energy. So in order to solve this, you have to calculate the eigenfunctions of this matrix here. This gives you this.
While solving on computer, we use this structure.
Yes, always. You always have a given Hamiltonian in terms of a matrix, and you do some matrix algebra. Use some library functions which calculates eigenfunctions and eigenvalues of a matrix. So what you end up with is you have the Hartree-Fock Hamiltonian. So this here is obviously our Hartree-Fock Hamiltonian matrix form. And what you have to do is, in the end, you have to solve H Hartree-Fock alpha beta times Ci beta sum over beta is epsilon alpha, epsilon times S alpha beta Ci beta. Why do I get here the S? Because S alpha beta is the overlap between the basis functions. So this is basis function alpha times beta by basis function. If you have plane waves, they are orthonormal and the S disappears. If you have Gaussians or whatever, then they are not orthonormal, the basis functions, and you have to solve H is epsilon times S. Okay. Epsilon alpha. So this is exactly the same as we did before, only that it's now in the matrix form. And you do the same. Again, so also here you have a Hartree-Fock Hamiltonian. The Hartree-Fock Hamiltonian acts on single particles. In this case it's a matrix, it acts on a series of expansion coefficients. The Hartree-Fock Hamiltonian again is not the many-body Hamiltonian. It's something which acts only on those single particle orbitals, which are given by the C. And the many-body wave function, our approximation to the many-body wave function, is the single slider determinant made out of the n solutions we have. So the next thing which we'll do on Friday is to answer the crucial question: is this a good approximation or not? No? Because so far we've only said instead of 10 to the 100 determinants, we use 1. We found an iteration for the energy. We now know which solutions we have to solve. We know what to do. But if we do it, is it good or bad? We do not know yet. So on Friday, you think it's good? Okay.
Because we have so much effort.
Exactly, we spent so much. So it is. Well, let me tell you the following. So with heart rate fog, one gets nearly always more than 90% of the energies, even typically 95%. Very often even 98% of the energy. So you get really the largest part, more than 90% of the energy. So this is good, it's not a bad approximation. The better part of heart rate fog is that these 1–2%, they are the ones which count. Because they are the ones which if you make a chemical bonding or which something, they are very crucial to saying one thing is more stable than the other. So you get the largest part of the energy, and often it is good, but most of the time it is not good enough. And so when we talk about the quality of heart rate fog, anyone has an idea what is the keyword which you've all heard many times, one tries to talk about? Correlation. Do you know what is the link between correlation and heart rate fog? So you see, you have courses on strongly correlated systems, and correlations here, strong, weak, everything, but no one has told you. What is the definition of correlation? Well, the definition, the very basic definition of what is a correlation energy is, it's the difference between the exact solution and the heart rate fog solution. Okay? So by its very definition, whatever is not in heart rate fog is the so-called correlation energy. Okay? So if you have strong correlation effects, if you have large correlation energies, it means heart rate fog is not a very good approximation. If we have very weak correlations, then heart rate fog is a good system. We will talk about a lot about this in the future. And heart rate fog is, we did all this work because heart rate fog is so important, because what everyone does is one always starts from heart rate fog and then one adds corrections to it. Okay? So because then someone told me once when I asked how shall we solve the problem, someone said perturbation theory. Well, perturbation theory can only be done on something which is weak. But if you now have a scheme which gives us 98% of the energy, then the rest might be weak. Yeah? So for example, perturbations on top of heart rate fog is something which a lot of people do. Okay? Okay, so see you on Friday, where we'll talk about correlations.
Yeah, it's just about.
Why?